Welcome to Advanced Quantum Chemistry and the 10th lecture on Hartree Fock theory. In this lecture we will discuss how the Hartree Fock equations are actually solved in a quantum chemical program. Now the Hartree Fock equations are integral differential equations. So they are differential equations, and it's actually possible to solve them numerically for atoms and in particular for diatomic molecules. But that's not the normal way how it's done in a normal quantum chemical program. In normal quantum chemical programs, one uses an approach which was derived by Roothaan, and that is we expand the unknown spatial orbitals in a set of known functions, chi, so-called basis functions. So we make the unknown spatial orbitals as a linear combination of this set of known functions with some unknown expansion coefficients. And these coefficients are typically called molecular orbital coefficients. Although one does the same also for atoms, and there of course there would be atomic orbital coefficients, but they are normally called molecular orbital coefficients. So this more or less actually corresponds to the LCAO approach from basic physical chemistry textbooks, the linear combination of atomic orbitals for making molecular orbitals, except that those functions are typically not really atomic orbitals, but they are some set of known functions. And in some of the other lectures we will discuss what kind of basis functions one actually uses nowadays. Now this expansion of the unknown spatial orbitals, and therefore the solutions of the Hartree Fock equation for spatial orbitals, is exact if the set of basis function is infinite. So if m is infinity, then this expansion is exact, and with such an infinite expansion in a basis set, we can then solve the Hartree Fock equations exactly, and the result would then be what we call the Hartree Fock limit. But of course, in any practical application, we cannot handle an infinite basis set, so we will always have to make an approximation by using a finite base set. And that means that we always are only solving the Hartree Fock equations approximately. So the orbitals we get out and the Hartree Fock energy are actually an approximation to the correct Hartree Fock energy and the correct orbitals. And that's sort of an extra approximation on top of the fact that the Hartree Fock equations and the Hartree Fock energy already is an approximation to the exact energy and the exact wave function. So we have this basis set approximation. Now inserting the expansion of the spatial orbitals here in the spatial Hartree Fock equations into the Hartree Fock equations, we do it here, here and also on the right hand side. And how do we actually solve this equation? How do we find these expansion coefficients? Because those are now the unknowns, these expansion coefficients. Now the way one does this, one multiplies from the left the Hartree Fock equations with another one of the basis function, and we do the complex conjugate, and then we integrate. And in this way we actually transform the differential equation, because the Fock operator still includes the kinetic energy operator, which is a differential operator. So although it looks like an eigenvalue equation, it is still also a differential equation. But now when we integrate here, multiply with another basis function and integrate afterwards, we convert the differential equation in an integral equation. Because what we have now here the sum over the expansion coefficients, and then we have here a sum of different integrals. And those integrals actually are just again elements of the Fock matrix, but now the Fock matrix not in the basis of its eigenfunction, but the Fock matrix expressed in the basis of these basis functions. And on the right hand side, when we multiply from the left with chi beta complex conjugate and integrate. Epsilon is a constant, the coefficient of course a constant. So what we get here is we get an overlap matrix of the basis functions. And the basis functions are in general not orthogonal, so this overlap matrix is not going to be a unit matrix, but it's going to be a real overlap matrix, and it's also sometimes called a metric. So if we write that now in terms of the elements of these matrices, here the Fock matrix in the basis of the basis functions, and here this overlap matrix, all the basis functions, this version of the Hartree Fock equations is called the Roothaan equations. And if you now not only look at one equation for the basis function beta, but we write up all the equations by using all the functions which we have in the basis set, then we end up having, and collect all these equations in matrices, then we end up with a matrix equation, a matrix version of the Roothaan's equation, where we here have the Fock matrix in the basis of the basis functions. Here we have a matrix where each column in this matrix contains the molecular orbital coefficients for one particular molecular orbital. Here we have the orbital energy matrix, we have this overlap matrix, and again this matrix of molecular orbital coefficients which are sort of column-wise, which are column-wise in this molecular orbital coefficient matrix. And then you can see that, I mean, this is an eigenvalue problem, but it's actually a generalized eigenvalue problem because we have this overlap matrix here, which in the eigenvalue problem here takes the role of a metric. So we have this generalized eigenvalue problem, and the way to solve this is we can calculate the Fock matrices, the elements of the Fock matrix, we can calculate the elements of the overlap matrix, and then we have to diagonalize that, and the eigenvalues are then going to be the orbital energies, and the eigenvectors are going to be our molecular orbital coefficients. We have to solve them iteratively, because in order to calculate the Fock matrix, I need to know the molecular orbital coefficients. But I only can get the molecular orbital coefficient which I have solved when I have solved this the Roothaan's equation. Now let's look at this Fock matrix in the basis of the basis functions. So here we have the Fock operator, the spatial orbital Fock operator, and we have this integral with two basis functions alpha and beta. Now the Fock operator, like always, of course, had a contribution from this core Hamiltonian, which is the kinetic energy operator and the operator for the interaction with the nuclear charges. These integrals then are collected in a matrix which is called the core matrix. And then we have here from the averaged electron-electron interaction with the Coulomb operator and the exchange operator. And since we're using spatial orbitals and use the restricted spatial orbitals, we get a factor 2 for the Coulomb and have just the exchange operator. And these integrals are collected in a matrix G. Now if you look a bit more at this H matrix, the core interaction matrix, as I said, it's integrals over the kinetic energy operator and integrals over the operator representing the interaction between the charge of the electron and all the nuclear charges. And this G matrix consists of something which looks very much like a Coulomb and exchange integral. But one has to remember, of course, the Coulomb and exchange operator. They include integrals over all the other orbitals, all the other occupied orbitals, and these are still spatial orbitals. So here we have, of course, the basis function chi alpha in the browser. It's complex conjugate we have here, and we have a basis function there, and here in the exchange version. But the electron 2 is still described by spatial orbitals phi here. And if you want to calculate this G matrix, of course, we have to insert now the expansion of now the spatial orbitals phi describing the other electrons. Due to the Coulomb and exchange operator, it depends on the spatial orbitals. Equation. So one has to, and that's what I've done here, inserted the same expansion in the basis function. Now we only have integrals over basis functions. And we have here the molecular orbital coefficients for phi j here expressed in basis functions delta, chi delta, and chi gamma. And it's the same coefficient we get from both integrals. Now this product of molecular orbital coefficients summed over all occupied spatial orbitals together with the two here, that actually forms what is called a one-particle density matrix. So that's a density matrix. So we can write the G matrix also in terms of this density matrix, where we have a contraction or multiplication of the elements of the density matrix with corresponding two electron integrals in the basis of the basis functions, here for the Coulomb and here for the exchange part. That all means that, as we know, the Fock operator depends, and having inserted these spatial orbitals here, the Fock matrix actually depends on the molecular orbital coefficients or on this density. But the molecular orbital coefficients, they are found as the eigenvectors of the Fock matrix. So the Fock matrix in the Roothaan's equations depends actually on its own eigenvectors. And that means we have to solve Roothaan's equation iteratively. And how that is done precisely, we will discuss in the next lecture.